Reality doesn't follow rules. Not always. Sometimes the universe just breaks them. December 2024. Physicists found a crystal that does something impossible. Cool it down and a magnet floats above it. Zero resistance. Perfect superconductivity. But here's the weird part. Cut it open, the inside is normal metal, regular physics. Only the surface, the outer skin, is superconducting. That shouldn't work, but it does. It's like your skin obeying different laws of nature than your bones. Let's find out why this matters. The material is platinum-bismuth. It sat in labs for years. Nothing special, just another metal. Until someone cooled it to near absolute zero and looked at the surface. They found something that breaks every rule of superconductivity. In normal superconductors, the entire material transforms, inside and out. Electrons pair up, resistance drops to zero. But this one, only the surface. The interior stays normal. The outer atomic layers become superconducting. Same material, same temperature. Two different states of matter separated by the width of a single atom. Researchers at ETH Zurich tested it over and over. Different conditions, different samples, same result. The surface electrons were pairing in the 6 forbidden directions that shouldn't be possible. Configurations that violate what we thought were fundamental rules. One researcher called it unlike any known superconductor. Translation: we have no idea how this works. For over 100 years, we've had one rule about superconductors. When a material superconducts, the whole thing changes. All of it. You can't have superconductivity on just the surface. That would be like water frozen on top while staying liquid underneath at the same temperature. But that's exactly what this crystal does. The surface exists in a different quantum state than the interior, one atomic layer apart. Physicists call this topological superconductivity. The shape and edges matter as much as the material itself. We predicted it could exist, on paper, in equations, but we'd never seen it in real life. Not like this, not this simple. Most exotic quantum states need extreme conditions. Temperatures a fraction above absolute zero. Magnetic fields stronger than stars. This crystal? Liquid nitrogen, $70 online. We found a material that breaks the rules using equipment from the 1960s. Here's why quantum computer engineers lost their minds. When electrons pair in these forbidden directions on the surface, they create something called Majorana particles. In 1937, a physicist asked, what if a particle could be its own antiparticle? For 80 years, it was just math. No proof. The surface of this crystal creates exactly those conditions. Electrons effectively split in half. Each half is the other's antiparticle. Every quantum computer built so far has one fatal flaw. The information decays in microseconds. Errors pile up. The system crashes. But Majorana particles are different. The information isn't stored in one spot. It's stored in the relationship between two particles separated in space. You can't accidentally destroy it by bumping one particle. You'd have to disrupt both at once. That's fault-tolerant quantum computing. The Holy Grail. We just discovered we can make as many as we want. Cut the crystal, polish an edge, create a boundary. Majorana particles appear. We're not hunting for rare events. We're engineering them on demand. We thought we understood superconductivity. We had rules, laws, patterns we'd observed for a century. Nature just showed us those weren't laws. They were just the only examples we'd checked. This crystal sat in labs for years. Ordinary, filed under studied, until someone looked at the surface. How many other materials are sitting in storage right now? Labeled, cataloged, assumed to be fully understood. The Platinum-Bismuth crystal was always doing this. We just weren't looking in the right place. Sometimes the breakthrough isn't finding something new. It's realizing we never fully understood what we already had. Research teams are already designing new materials, artificial surfaces, controlled edges. The question isn't if we can build fault-tolerant quantum computers. It's how fast. What else are we missing when we assume the rules are fixed? I'm Mind Mechanics Studios, where we fix what you didn't know was broken. The most important discoveries don't always announce themselves. Sometimes they've been waiting in plain sight.